Hi everyone, I am Ankita Bakshi and I'm a product engineer on the spatial statistics team here at Esri Redlands. The Esri Ocean Weather and Climate GIS Forum is one such place where I can candidly talk about climate change and its impacts. So here I am taking this opportunity to draw your attention to the increasing wildfires in the state of California in this era of climate change. To begin with, on this map, we are seeing the Cooperative Observer Program or COOP stations, which collect daily weather information throughout the state. I'd like to thank NCAR and UCAR for providing the daily temperature and precipitation data recorded at these stations from 1950 to 2004. The data was initially stored in a NetCDF format, which is common for such type of multidimensional scientific data. So step one was to take these net CDFs and create feature layers with maximum daily temperature and precipitation values using the Make Net CDF feature layer tool. The resulting layers each contain about 13 million daily observations for a period of 54 years. To find patterns in temperature and precipitation, step two was to aggregate the daily observations into an annually aggregated spacetime cube. The Create Spacetime Cube from Define Locations tool lets me specify the temporal scale at which I want to aggregate my data. And just by simply putting the spacetime cube in 3D, we start seeing some obvious spatial patterns. Like the coastal areas have lower maximum daily temperatures than the inland regions. However, to understand how the temperature values have changed over time, in step 3, I use the trend analysis option in Visualize Spacetime Cube in 2D tool, which runs Menkendel statistics at each location to find significant trends. The darker purple locations show an overall upward trend in the maximum daily temperature values, while the darker green locations show an overall downward trend. And when I add California fire perimeter layer with my temperature trends, we start seeing co-location of wildfire boundaries with increasing trends in temperature. And when I add precipitation to this equation, it reinforces the fact that, in fact, these locations are getting hotter and drier, making a perfect recipe for wildfires in the state. If you have attended the Ocean Climate and Weather GIS Forum before, you might have seen similar trend analysis in Spacetime Cube, which helps us uncover the historical patterns in the data. What I'm excited to show you next is a new set of capabilities that will enable us to look to the future and do forecasting. Recently, in ArcGIS Pro 2.6, we introduced a whole new toolset for time series forecasting, ranging from some traditional modeling methods like curve fit to more sophisticated machine learning approach like forest-based and exponential smoothing. Let's first look at curve fit forecast. In curve fit forecast, you can fit these parametric curves to your data and do forecasting. For my input spacetime cube, I created a new spacetime cube with monthly aggregation to capture the subtleties of monthly trends in temperatures. I have forecasted for the next 24 months and let the tool auto-detect the best curve type out of linear, parabolic, exponential, and S-shaped for each location. One of the parameters that you will see in all of these forecasting tools is the number of time steps to exclude for validation. In forecasting, it is critical to know how well of a forecasting job your model did by comparing the raw values with the forecasted values. And this type of validation is just built into the tool. The output of the curve fit forecast gives me the last time step of the time series forecasted values. One of the most important and one of my favorite outputs of this tool are these pop-up charts that the tool automatically creates. So for each location, the blue dots represent the actual recorded temperature values, and the forecasted values are shown in orange. As we can see that a simple forecasting method like curve-fit did not do a great job of capturing the complex patterns in the data. So I'll use another forecasting model, exponential smoothing forecast, which works really well with cyclical patterns and trends in your data. So I've again forecasted for the next 24 months and excluded 10% of data for validation. Since this method is recommended for seasonal data, here you can specify the season length in your data. However, if you don't know about this value, you can also leave it blank and let the tool find the season length for each location. And when I look at the output of this tool, we can see that this model was able to capture the complex trends and patterns in the temperature values better, with the orange values being the forecasted values and a confidence interval around the forecasted values. The tool was also able to detect 12 months as the season length, which makes perfect sense for a monthly aggregated temperature data like this. I also ran forest-based forecasting model, which uses random forest under the hood to train the model and do the forecasting. And here also, we can see that the tool was able to capture the complex trends. But how do I know if exponential smoothing did a better job of fitting the model at each location than forest-based models? And in trend analysis, we saw how different locations had different upward and downward trends and patterns. So it's possible that a single forecasting model doesn't work for all the locations. So how do I find out which model fits better at each location? The answer to that question leads me to another awesome capability of this toolset, which is to evaluate forecasts by location. So I took forest-based forecast, exponential smoothing forecast, and curve-fit forecast results and put them in this tool to find which model fits the best at each location. The output of this tool shows me that exponential smoothing was chosen for many locations in Southern California, and forest-based performed better up in the north. As a geographer, it is so fascinating to be able to capture and model these hybrid results. And even if time series forecasting isn't explicitly spatial, you start seeing these spatial patterns in your data just by looking at which model gets chosen. And as we model and forecast the weather conditions into the future, it can help us with a better understanding of what fire risks might look like in California. As an impact of climate change, the weather we are experiencing is changing dramatically. The norms that we are used to are quickly fading away, and we need to be able to have these sophisticated methods that could help us describe and predict the patterns in the future. Thank you.